And this terminology allows us to more clearly distinguish between a relation that is a function and a relation that is not a function. So let's look at a simple map diagram. So for a relation to be a function, we must have that an element in the first set is mapped to a single element in the second set. Now, it is perfectly fine if there are two separate elements in the first set that are mapped onto a common element of the second set, then we still have a function. It is also fine that there is an element in the first set that is not mapped into the second set, and it is also fine that there are elements in the second set that are not mapped onto at all by any of the elements in the first set, and we still have a function. This is a function between the sets A and B. Now, if instead a single element in the first set is paired with two separate elements of the second set, then we have a non-empty relation, but this relation is not a function. So in this map diagram of the function between A and B, if we call the function phi, then this function consists of two ordered pairs, the ordered pair A1, B1 and A2, B1. Okay? So new definition. Let phi be a relation or be a function between the sets A and B. The domain of the function is the set, which we denote DOM phi, and this is the set of those elements in the first set for which there exists an element in the second set, such that the ordered pair is in the function. So I've used some notation that I have not used previously, so let's look at those elements. The backwards letter E, capital letter E, means there exists. This is known as the existential quantifier. This symbol here means such that. And so again, the domain of the function phi is the set of those elements in the first set for which there exists an element in the second set such that the ordered pair is in the function. The range of the function is the set that we denote RNG of phi, and this is the set of those elements in the second set for which there exists an element in the first set such that the ordered pair is in the function. So using the example function that contains the two elements, or the two ordered pairs, A1, B1 and A2, B1, the domain of this function is the set which contains the elements A1 and A2, because these are the elements in the first set for which there exists an element in the second set, such that the ordered pair is in the function. And the range of this function is the singleton set, singleton meaning a set which contains one element, and so the range of this function is the singleton set containing the element b sub 1, because this is the set of those elements in the second set such that there exists an element in the first set such that the ordered pair is in the function. So now we can refine our properties of a function and define a new function. So let phi be a function between the sets A and B if the domain of the function is the entire set A. Then this function phi is a function from the set A into the set B. And this is denoted this way. And this is red. Phi is a function from A into B. So once again, let's look at a map diagram to clarify this definition. So for a function from A into B, we must have that each of the elements in the first set is mapped to a single element in the second set. Now, once again, it is fine if there are two separate elements of the first set being mapped into a common element of the second set. And it is also fine that we have an element in the second set that is not mapped onto, and this is still a function from the set A into the set B. And in this case, the set A is called the domain of the function, since we are requiring that that the domain of the function be the entire first set. And the set B is called the codomain. Now, with a function from a set into a second set, we generally do not show by explicit ordered pair notation that a given ordered pair is in the function. Rather, we use functional notation and say that phi of A is the element B. Okay? So now we will further refine our conditions and define a new function. The function phi from A into B is an injection or injective function if every element in the domain A is mapped into a unique element in the codomain B. So once again, let's look at a simple map diagram to clarify this definition. For a function from A into B to be an injection, each element in the domain A must be mapped to a unique element in the codomain B. Now once again, it is fine if there are elements in the codomain B that are not mapped onto, but we must have that each element in the domain is mapped to a unique element in the codomain. In other words, we can no longer have the situation where two separate elements are mapped to a common element. Each element must be mapped to its own unique element in the codomain. So notice that we can restate the definition this way. The function phi from A into B is an injection if and only if the assumption that phi of A is equal to phi of B implies that the arguments A and B are the same. And this is how we prove that a function is an injection. We assume that phi of A is equal to phi of B and show that this leads to the conclusion that A is equal to B. So let's look at an example first of a function that is not an injection. The function phi from the set of integers back into itself, defined by phi of A is equal to A squared, is not an injection. And we'll show this by counterexample. Notice that phi of -1 is the same as phi of 1, which gives the element 1, but -1 is not equal to 1, and so the function phi is not an injection. So now let's look at an example that is an injection. The function phi from the integers back into the integers, defined by phi of A is 2 times A, is an injection. So proof: suppose that phi of A is equal to phi of B, then 2 times A is equal to 2 times B, and so A is equal to B, and therefore the function phi is an injection. Okay, so now we will define a new function. The function phi from A into B is a surjection or surjective function if every element in the codomain B is mapped onto by at least one element in the domain A. So let's look at a simple map diagram. So for a function from A into B to be a surjection, each of the elements in the codomain B must be mapped onto by at least one element in the domain A. Now notice here that we no longer have an injection because there are two separate elements in the domain being mapped onto a common element in the codomain, but we do have a surjection because each of the elements in the codomain are mapped onto by at least one of the elements in the domain. Now, because each of the elements in the codomain are mapped onto by at least one of the elements in the domain, a surjection is also called an onto function. So notice that we can redefine a surjection this way. A function phi from A into B is a surjection. If and only if, given an element in the codomain, this implies that there exists an element in the domain such that the element B in the codomain is phi of that element in the domain. And this is how we prove that a function is a surjection. We show that for every element in the codomain, there exists an element in the domain such that that element in the codomain is mapped onto by the element A under the map phi. So let's look at an example first of a function that is not a surjection. The function phi from A, from the integers back into the integers defined by phi of A is 2 times A is not a surjection. Now we have seen that this function is an injection, but it is not a surjection. And we'll show this by counterexample. Notice that the number 1 is in the codomain, which is the set of integers. And there does not exist an element A in the domain, which is also the set of integers, such that 1 is mapped onto, under the map A, by any integer A. That is, the number 1 is not equal to 2 times A for any integer A. And so the function phi is not a surjection. So the problem that we have with this function not being a surjection is that there are elements that are not mapped onto by this function. And so let's now define a function that is a surjection. The function phi from the integers into the even integers defined by phi of A is 2 times A is a surjection. So proof. Let the element B be in the set of even integers, that is the codomain of this function, then this element b is 2 times a, where a is any integer. That is, for every element b in the codomain, which is the set of even integers, there exists an element in the set of integers, which is our domain, such that that element b is mapped onto by that element a. And therefore, the function phi is a surjection.